Alright, this is Group B25 doing a presentation on relations representations. And our group members are Anurup Arora, Zachary Berg, Rachel Chow, Dominic Rona, and Omid Gomeshi. And please, if you enjoyed our video and want to learn more about discrete mathematics, visit noatom.com for more of the same. Alright, so an introduction. What is a relation? A relation R is a subset of A cross B, and it's a generalization of a function. Now, what is R? It's a set of ordered pairs xy, and these xy are elements of A cross B, where A and B are different domains, or similar domains. For example, if A and B are the domain of integers, then we can say that R is a set of pairs where x is greater than y. So for example, you'd have the pairs 2, 1, 3, 1, 3, 2, etc. Now, a relation between finite sets can be represented using a 0, 1 matrix, and we can represent this using an m by n matrix of Boolean values 0 and 1. So let's see how this works. Now, suppose R is a relation from A being the set or the domain from A1 to AM, and B being the domain from B1 to Bn, where n and m can be equal, but this is just a generalization. Then we say our MR is a cross product of these. So you have M11 through Mij. And that's your matrix. So where does the Boolean relation come into play? Well, these ordered pairs represent every pairing that can happen between A cross B, but only some of them, or all of them, can be in your relation matrix, part of the relations, based on whatever stipulations you're given. So a certain element is either in your relation matrix or not, and you denote this with 0 and 1s. So, for example, in our earlier example of using integers, if R is a relation between integers cross integers where x is greater than y, then 1, 1 would not be in your matrix because 1 is not greater than 1, so you'd put a 0 there. But 2, 1 is, so for the position of 2, 1, you would put a 1 there. Now let's see an example of how this works.
For our first example, suppose that we have a set A, 1, 2, 3, and a set B, 1, 2. We let R be the relation from A to B containing the pair AB, where A is greater than B. We try to find the matrix representing R if A1 equals 1, A2 equals 2, A3 equals 3, B1 equals 1, and B2 equals 2. Because the set R equals 2, 1, 3, 1, and 3, 2, the matrix for R is represented as follows. The ones in the matrix show that the pairs 2, 1, 3, 1, and 3, 2 belong to R, and the zeros show that no other pairs belong to R.
Alright, and coming back, let's do a review of properties of relations. So, reflexivity, this one's pretty simple to understand. It's just saying for any x, R of xx, or xx is in your relation. So if you have, for example, 1, 2, 1, 2 is in your relation, then 1, 1 and 2, 2 must also be in your relation. Irreflexivity is saying the opposite for any x, not R of xx. So, using our previous example, if you have 1, 2 in the matrix, you don't have 1, 1, and you don't have 2, 2. Now, transitivity, this one says for any x, for any y, and for any z, if R of xy and R of yz, then R of xz. So, if you have 1, 2 and 2, 3, then you also have 1, 3. Now, symmetry. Again, this one's pretty easy to understand. For any x and for any y, if you have R of xy, this implies that you have R of yx. If you have 1, 2, then you have 2, 1, and vice versa. Now, asymmetry says for any x and for any y, if you have R of xy, this implies that you do not have R of yx. So the opposite of symmetry. If you have 1, 2, you cannot have 2, 1. But antisymmetry is saying if, for any x and for any y, if you have R of xy and R of yx, then x must equal y. Now this brings a fine point between asymmetry and antisymmetry. Asymmetry, by definition, can't have the pair 1, 1 because obviously you can't have yx if you have xy, but antisymmetry says if you do have this pairing, then x must equal y, which holds true for 1, 1, 2, 2, all the way through I. So let's look. How do we represent these using matrices that we spoke about earlier? Well, R is reflexive if the main diagonal of MR is all 1s. And this is pretty simple. So for all I, MII equals 1. What is that saying? Well, let's use our example of integers earlier. If your matrix is the cross between of integers with integers, then it's reflexive if every position down the diagonal, which would be 1, 1, 2, 2, 3, 3, 4, 4, if those are all true and part of it. Now, it's irreflexive if the main diagonal is all zeros. And again, this is pretty easy to see. A relation is irreflexive if it has no pairings, if for all x, R of xx is not in the matrix. So, if we use our integer example, 1, 1, 2, 2, 3, 3 could not be part of that relation, so you must have a 0 there. But this brings a fine point. A matrix can be neither reflexive nor irreflexive if the diagonal values are mixed. So if you have some 1s and some 0s, that matrix isn't reflexive because it doesn't contain every pairing of II, and it's not irreflexive because it does contain some pairings. Now, let's look at symmetry. Matrix is symmetric, or a relation is symmetric if its matrix representation has 1s, where for every ij, m of ij equals 1 implies that m of ji equals 1. And the same thing for 0. If m of ij is 0, then m of ji must be 0 to have symmetry. And it's antisymmetric if for any ij, m of ij equals 1 and m of ji equals 1 implies that I equals j. So you can actually have symmetry and antisymmetry. In what case? Only in the case where the only values you have that exhibit the property of symmetry are the main diagonal. In other words, it has 1, 1 and 2, 2, but it doesn't have, if 1, 2 is true, and in your matrix you can't have 2, 1. That's a case where they're both true. So, and finally, R is transitive if for any ijk, m of ij equals 1 and m of jk equals 1 implies that m of ik equals 1. This is hard to see looking at a matrix, but by definition of transitivity, this property makes sense. Alright, and finally, let's move on to digraphs, or directed graphs. And what is this by definition? Well, a digraph consists of a set of vertices or nodes together with a set E of ordered pairs of elements of V called edges. The vertex A is called the initial vertex of the edge, AB, and the vertex B is called the terminal vertex of this edge. So this is different from a simple graph or a non-directed graph where the edge between two nodes goes both ways, or you don't have this set of direction. Now your initial point, or your initial vertex, is pointing to your terminal vertex. It doesn't go both directions. So just because you have AB, it doesn't imply that you have BA. Now let's move on to a few examples that illustrate this property.
In this example, we will be looking at the directed graph of R on the left. We know that this graph is reflexive because there are loops at every vertex. We know that this graph is neither symmetric nor antisymmetric because there is an edge from A to B, but not one from B to A, and because there are edges in both directions connecting B and C. Finally, we know that R is not transitive because there is an edge from A to B and an edge from B to C, but no edge from A to C.